Want to write a network client for the Commodore Amiga, but don't know where to start? This video's got you covered. Come on, let's get our paws dirty and write some C code. Wait, we're doing this one in assembler? Older machines don't have a lot of processing power. The Motorola 68000 processor in the earliest Amigas only ran at about 7 MHz. Depending upon your goals, writing your program in a higher level language like C might make the program too slow. These languages also create larger binaries, and in the days of 880 kilobyte floppy disks, every byte matters. The server I wrote in the last video was very simple. It bound the socket to a hard-coded port, and waited for a connection, printing out whatever it was sent. For the client, I want a bit more flexibility. I want to create a netcat-like tool for sending a string of data to any IP address and port. I'll be writing all this code right on the Amiga, rather than using cross-compilers or emulators like Vamos. I want to keep it as retro as possible. And if you want to keep it retro too, you can use an assembler that runs right on your Amiga. AsmPro is an assembler, editor, debugger, and monitor used by demo scene coders. Like with C compilers, you have to set up the Amiga native development kit headers for use with AsmPro. This requires setting up an AsmPro assign, creating an includes folder in the place where you unpacked AsmPro, copying over the contents of the include_i directories over to the includes folder, and copying over the FD directory to the AsmPro folder. When working with AsmPro, there's a few things I needed to keep in mind. One was to ensure that when I'm adding an include directory path using incdir, that the path has a terminating slash in it. Another is to create a macro for building references to the various functions that Amiga OS provides. AsmPro is a macro assembler, which means you can create macros, blocks of code that can be modified and copy-pasted dynamically into the code right before it's assembled. For the Amiga, you need to define a funcdef macro. The exec/libraries.i header describes exactly what you need to do, but AsmPro needs a slight tweak. This macro creates a bunch of constants that start with _LVO that let you call Amiga OS library functions. While AsmPro is pretty great, if you're new to assembler, like I kinda am, having a place to try out assembly language routines quickly is helpful. In the description, I've linked to a web-based 68000 assembler, which I've used to get a handle on how assembly language and parts of the processor work. Of course, it can't execute anything Amiga related, so no Agnes, Denise, or Paula, or any Amiga OS functionality, but if you're trying to figure out how all the 68000 assembler commands work, then it's super helpful. Speaking of, I'm going to cover just enough 68000 assembler to make this client work. As usual, I've linked to the source code, as well as a version of the program in C, in the description. Grab the code and follow along. A computer's processors, or CPUs, main job is to move data around and transform it in different ways. The CPU can read from and write to the memory contained within the computer. If you're doing this a lot, it can get kinda slow. Most CPUs will have a little bit of memory on them to hold values for faster processing, or to keep things better organized. This onboard memory is organized into slots called registers. On the 68000, there are 16 registers. 8 of them, data registers, are for raw data, and 8 of them, address registers, hold an address to a part of memory. The last address register is used to store a reference to what's called the stack, where you can shove some data onto to retrieve later. There's also a status register that helps with math and conditionals results. Speaking of memory, a 68000 assembler makes it easy to reserve some memory in your program for storing stuff. The ds, dc, and dcb commands allow you to reserve spots in your program where data lives. They actually become part of the executable that's outputted, and when you modify them, you're technically modifying an area of your program, so be careful. So, how do you access this memory? The 68000 provides a bunch of different ways of picking which part of memory you want to access, based on the contents of an address register. You can access the memory at the address in the register, kind of like a pointer in C. You can take that address and add or subtract the value, then access the memory at the result. You can take that address and add or subtract what's in a data register, a more dynamic version of the last approach. You can increment or decrement the address in a register when accessing the memory. You can even use a raw number that points to a part in memory to read. You do this a lot when working with the exec library. There's some other modes, but we're not using them in this program, so we'll maybe get to them in a future video. You also need to tell the 68000 how to move data around in memory. For this, you use the move command. There's a couple of flavors of the move command, especially when you're moving data into address registers. When you're dealing with blocks of data you've allocated, or with locations in the program code itself, you'll be working with labels. Labels get turned into the actual byte position in the assembled code. When working with literal values like labels or constants, you have to tell the assembler to use the raw value, rather than trying to look up a memory address. For this, you use... Hey, is it a hashtag or a pound sign? I'll just use hashtag. Maybe that'll help with search results. When you use hashtag number, you mean that number. When you use hashtag name of variable, which is really hashtag label, you mean that address within your program. This allows you to make subroutines you can jump to as well. For one of the BSD socket functions, we're going to need a data structure. In C, you define those with struct, but in assembler, you're on your own. For this code, I've chosen to create a data storage of the correct size, then create constants that map the positions within that data storage, and I'll use indirect displacement addressing to target spots in that storage. Finally, we're going to need to compare some values. The 68,000 lets you compare values from various places to a data register in various ways, setting status register bits as you do so. We'll use the status of those bits to jump to different parts of our code. Pretty much everything our client is doing uses Amiga OS functions rather than hitting the hardware directly. The important information we need in order to use Amiga OS functions are the library vector offsets for the functions you want to call and what registers need to contain what data. Library vector offsets, or LVOs, are the data positions from the start of the library that tell programs how to access individual functions. Once you have one of these negative numbers, you tell your code to jump to that address, which causes you to jump to where the function actually lives in memory. As for knowing what to put in each register, the documentation for the Amiga Native Development Kit describes which function parameter corresponds to which hardware register, and, once complete, where the function stores its return value. Amiga OS uses the A6 register to handle function calls. You load this register with the base of the library you want to call, and then you use indirect displacement addressing to call the appropriate function. This is such a common operation that the JSR -number parentheses A6 is replaced with an official macro called calllib. The assembler headers in the NDK are a little incomplete. Most of the interesting functions in the DOS library don't have LVOs. Also, we need the LVOs for the BSD Socket Library. Remember that FD directory from earlier? FDs in Amiga speak are function definition files, and they define the library's functions and parameters. The order of the functions in the file determine the numeric value of the LVO. We can use a tool called FD to Pragma to create our own assembler include files for the DOS and BSD socket libraries. Working with AsmPro is a little different from a purely command line compiler or assembler. When you start the program up, you're presented with a blank console. If you look through the menus, you'll see a lot of options. Don't worry, you're only going to need a few of these to get started. AsmPro comes with an editor, but I prefer to use an external editor. Once you've saved your assembler code, type R in AsmPro and hit enter to bring up a file selector. Choose your source code and AsmPro will load it into memory. Then, type A and hit enter. AsmPro will assemble your code and alert you to any errors. Once you've fixed up your errors, type WO and hit enter to save out an executable you can run in the shell. AsmPro also comes with a debugger. Once you've loaded your source code, hit Amiga D or use the menu to get to the debugger. Hitting the down arrow key steps through your code one command at a time. You can set a breakpoint if you want to stop execution at a particular location in the code. You can also watch parts of memory for changes, and the current register status is displayed in a window on the right. Be sure to zap watches and breakpoints if you've changed your source code and reassembled, as those watches and breakpoints will persist between disassembler runs, and the memory addresses they originally pointed to will likely have changed. Finally, since the likelihood of you crashing your Amiga is pretty high, be sure to save your work often, and ideally back it up. My Mister, where I do this development, has network access, so I can FTP files to an internal FTP server after I hit a milestone in development, just in case something goes really wrong. Alright, now let's get into some code. We start by opening up the DOS library. We do this via the exec library's open library function. Exec is a library that is always open and accessible, and the pointer to the exec library always lives at memory address 4. To open a library, we put a pointer to a null-terminated string that contains the library name in A1, and the minimum version of the library we want in D0. We then put the contents of memory address 4, which always points to the base of the exec library, into A6, and we call open library using the appropriate LVO. Remember that calllib_LVO expands to JSR_LVO parentheses A6. If we were able to open the library, the base address of that library is put into D0. If not, D0 contains the number 0. If we're unable to open the DOS library, there's really not a lot that we can do, so we have to exit the program. we set a really scary exit code and jump to the teardown section. The teardown section removes the need for duplicating the code necessary to free resources at each failed branch. We'll get to how that works a bit later. Once the DOS library is open, we open the BSD Socket Library. We use the same approach, only this time, if the opening fails, we can print a helpful message to the user by using the DOS library. The DOS library has a function called putStir that lets you print a string to the console. You put the address to a null terminated string you want to print in D1, and you put the base to the DOS library into A6. When you call the function, the string gets printed to the console. In this case, we can print a message saying we couldn't open the BSD Socket Library, suggesting that the user start up their internet connectivity software. We'll be printing a lot of strings, so we can wrap this code up in a macro to make it easier to call. Since this client is going to act a lot like netcat, we'll need to potentially take in a lot of text from the user. While we could allocate that data using storage statements in the code, let's get some more practice with Amiga OS and use allocmem to reserve some RAM. The Amiga has a few types of RAM, the most important type being chip RAM, which the custom chips use for their special functions. Since we just need RAM to store what the user typed into the command line, we don't care where the RAM comes from. We do want to clear it out with zeros to start though. The NDK headers provide constants for working with memory functions in the exec/memory.i header. We define a constant indicating the size of the buffer we want and use that constant to populate D0. We use another constant to pass the mf_clear flag to D1. Then, we call the allocmem function on the exec library. If we get back 0 in D0, we know our memory allocation didn't work. Otherwise, D0 contains the address of the allocated RAM, and we store that in a variable of our own. Now, it's time to read command line arguments. We'll have two, the IP address and the port we want to connect to, plus any additional words that the user typed in as their message. For this, we'll use the DOS library's readItem function to pluck the first command line argument off of the list. Technically, command line arguments in Amiga OS are part of a command's standard input. readItem defaults to reading the first word-like thing from standard input and placing it into a buffer, the address of that buffer placed into D1, and limiting that read to a certain number of characters, D2. We'll leave D3 as 0 to read from standard input. If we get back nothing, or an error code, we'll print a message telling the user the proper format for executing the command. The first parameter is the IP address. We'll need to turn this string into a number we can use for our future socket connection. We do this by calling the BSD Socket Library function inet_adder. A0 gets the address to the buffer we just populated via readItem. D0 will receive the IP address as a long number, or -1 if the parsing fails. Next, we read the port. The port is a number from 0 to 65,535. We use readItem again, and then we can use the DOS library function stir_to_long to convert our string to a 32-bit value. We really only need the bottom 16 bits of this number, so if our number is bigger than that, we let the user know. Finally, we read the rest of the command line arguments. Since we're reading from the Amiga equivalent of standard in, we can create a loop where we read characters from this input one at a time until we hit the end. This small routine places the address of the memory we allocated via allocmem into a variable called fgetC location. We'll read a character from standard input using the DOS library function fgetC, and we'll check if what we've read is an end-of-file character or a carriage return from the user hitting the enter key. If it's either of those, we'll finalize the data we've read and move on. Otherwise, we'll add that character to the address currently stored within fgetC location, and we'll increment that address by 1. We also need to keep track of how many characters we've read in. When we're done, we'll store that count in read buffer length. We're ready to create a socket and try connecting it to a server. The socket function in the BSD Socket Library defines the type of socket we're using. We'll use the values from the BSD Socket Library headers for registers D0 through D2, and when we call the function, we'll get a socket identifier back in D0. Let's sanity check all of the values we've received so far. The exec library has a function called rawDoFormat, which is the equivalent of sprintf in C. To use rawDoFormat, we have to have the address of a formatting string in A0 and the list of things to print as a stack of items that A1 points to. We have a memory area, doFormat buffer, with enough room to hold plenty of arguments. We place them, one at a time, into the buffer using moves and a post increment to A1, which will increment the value by how large the data type happens to be. We need to give rawDoFormat a routine that sticks a character onto the output buffer. This uses loadEffectIvAddress to specify a piece of code that places that character onto the buffer, then returns back to rawDoFormat. Finally, we give rawDoFormat the address of the buffer we want to write to, which is passed into our routine. We can then use our putstir macro to print out the result of the formatting. Now, let's talk to our server. The BSD Socket Library connect function takes a struct defining our connection. The struct is 16 bytes long, but we don't need them all for an internet connection. We use indirect displacement addressing and the offsets of the different struct values interpreted from the C headers to populate the data structure with the type of connection, the port, and the IP address. We then pass our socket ID as D0, the length of our structure as D1, and a pointer to the structure itself as A0. Then, we call connect. Getting a 0 in D0 means we're connected. Let's send our data. Like with connect, the first parameter of the BSD socket send command is the socket ID. Send takes a data buffer pointer in A0 and the length of the data to send in D1. You can give optional flags to send in D2, but we're not doing that, so we'll move a 0 into D2. Once we call send, we'll see that the data from the Amiga gets printed on our waiting netcat server on my Linux machine. Send returns the number of characters sent in D0 or -1 if there was an error. Provided everything went well, we now tear down everything we set up. If we created a socket, we close our socket by calling close socket. If we allocated memory using allocmem, we free it using freemem. If we opened libraries, we close them with close library. If anything along the way set an exit code, we put that into D0 and then exit the program. We did it! We wrote a small Amiga program, purely an assembler, that uses built-in and internet stack provided functions to make a connection to a server and send along a string. Here's a comparison between the assembler and C versions of the code. The C code is a bit easier to read at a glance, but it also produces a much larger binary file. You know, it's good to know assembler, even just a little, if you're writing code for retro machines like the Amiga. Sometimes you need the reduced overhead. Sometimes you need to make smaller binaries. And sometimes assembler is your only option.